connecting a variety of remote, reasonably small, sometimes not devices through global network into the central system that receives signals from those devices, usually some measurements, and then do some processing and send the data back. So basically three distinguished sort of areas when it comes to technical stack. It's in the middle, global network connectivity, that's what connects those devices that measure stuff to the central systems. Obviously the sensors and devices, that's another group, and the central systems and implementation and central systems and applications that process that data and generate signals is the third component of it. So the sensors, is a variety of those, come from very small ones like measuring pressure, measuring flow, measuring temperature, etc., into more complex systems that measuring things in the cars as they operate, so-called connected cars, to smart utility meters, through actually mobile devices, because mobile devices now, like phones, laptops, phones and the tablets, now kind of belong to this IoT category as well. The connectivity is interesting. People think that internet will connect everything these days and it's sort of global, but when it comes to the Internet of Things, it turns like internet connectivity cannot be relied on in many use cases. So oftentimes people put in place different dedicated network to connect devices, especially when it comes to more critical applications like in military and etc. Also, the internet connectivity and Wi-Fi and IP in general is very resource consuming, and devices are often so small that they can't afford to have any IP stack on them and cannot afford proper encryption on those devices. So as a result, oftentimes we use protocols which are more energy efficient and very low throughput in the field, and then have a gateway which actually gateway to IP and then connect through internet or any other media to the central systems. I'll speak a little more about it. And in the end, we develop applications based on it, which is depending on the verticals that we're working with. It may be more efficient routing of trucks or more efficient fuel consumption. It may be predicting the failures of the machines and etc. Or it may be certain tracking of objects across the world. And the good examples of Internet of Things application would be things like Nest thermostat that many of you might have at homes. They're basically devices connected through Wi-Fi through your router and reporting the temperature and various measurements back into the central systems, and then the central application, as it collects this data, provides a certain insight in terms of energy usage and try to help controlling the energy use at home to optimize it to reduce the cost of heating your house. And various activity tracking devices also considered Internet of Things these days, and even though they may not be connected to internet all the time and only asynchronously through computer or Bluetooth when it's enabled, they consider Internet of Things as well. So in every industry, in every area of our life, we can have Internet of Things applications. In retail, they can help us measure track inventory. In the agriculture, they can control where there are cows are in this case, or how the animals migrate from one area to another, and etc., etc. So pretty much any applications, any industry can find applications of Internet of Things. Now, there's usually two ways how businesses look at the Internet of Things and evaluate how to make money of it, and it depends what the driver is. When the driver is to do the same thing as we do today, but more cost efficient, like when we operate manufacturing machines, we still operate them, but we want to optimize certain settings and certain modes of operations. Those are sort of a bottom line deployments when we reduce our running cost, our operational cost, and we basically achieve cost efficiency. Another group of deployments would be deployments in the new product life cycles, where we basically generate new revenue streams. For example, the Nest thermostat, a completely new product that generates total new revenue stream. The Fitbit and whatnot, those are totally new products. So it helps us to position those projects better as we embark on them. So that's very general 5 minutes introduction to what the Internet of Things is about and where we see the applications of those. I don't think I need any more than that. So what I want to move into next is to show you general sort of architecture, how kind of generic traditional Internet of Things stack would look like. So first of all, let's see if I have a mouse here. There we go. So first of all, there are sort of devices, and depending on what we're doing and how big are those devices, we might have those devices connected directly to Internet. As an example, one of our clients is Sonos. And Sonos is basically their speaker that's connected to Internet, that's streaming music, and you choose what you stream and etc. Connected to Spotify, Pandora, Beats Music, and whatnot, various radios, and so on. So that device is capable and powerful. It connects to the power outlet, and as a result, it has plenty of energy, so it's always connected through the Wi-Fi. Other type of devices that can connect directly to Internet would be our mobile phones, right? Because they usually have enough power in their battery to be, well, we wish that they would stay on the whole day connected to like 4G and LTE. Unfortunately, that doesn't happen, but the design is like that, right? So those have enough battery power to be always connected. Cars can always be connected as well, because they have obviously plenty of power in them. Other deployments is we have sensors which are really small and tiny. They may be connected through Bluetooth to a central hub, which will then route the packets through Internet to our central systems, or they can be connected even more power energy efficient protocols, because Bluetooth is actually quite draining on the batteries, even the newer versions of it. And there's a newer protocols which are very resilient, but very low bandwidth, like 1 kilobyte per minute type protocol, because sometimes you don't need as much throughput, but you need resilience and super low power that you can have a tiny footprint device mounted somewhere that's powered from like really tiny flat battery, like a tablet style and battery, and would be then connected to a hub. It's often called like a field hub, and then that hub would then route it through IP protocols to the central systems. In terms of the protocols between the field hub and the central system, currently two most common protocols in the Internet of Things, but they are more available. HTTP and HTTPS, of course, is the one of common protocols, but unfortunately it's not a very good fit because it's a sessionless protocol, because it's quite expensive to encrypt it, and it's also providing a lot of overhead in terms of big, huge headers and etc. A more efficient protocol that's commonly used, or most commonly used at scale, is MQTT protocol, which have really 2 bytes overhead per header, so it's much more a lightweight protocol. So oftentimes our system would include like an MQTT gateway on the ingestion as well. And then we have some sort of event bus, but because what often happens is that as those devices connecting to central systems and send the events in, we don't really want those devices to be stacked at any time and not able to sort of proceed further. We want to accept those messages as quick as possible and then process them. So this asynchronous processing is pretty common. There's pretty much no 100% real-time Internet of Things processing in those use cases, at least not centrally, and simply because it's difficult to guarantee resilient connectivity between the field and the center, so there's no point doing that. So those would be asynchronous, and it's usually some kind of event bus that's put in place. And then from there we have consumers of those events, and oftentimes there's 2 types of consumers. One of them would be some real-time processing tool, and I'll give you examples of those, and then another one would be sort of a long-term storage for analytics and long-term store, as well as to power certain apps, whether it's through web interface or communicating their insights and data back into the devices if they have the ability to also change their behavior or display something like Nest thermostat can display some of the statistics that may be calculated centrally. So this sort of control system is the one that's designed to take signals either from real-time processing framework or from other app, which it didn't actually draw here, and then send the signal back to the end devices. If it's sort of end devices with sensors or if it's device centrally in the field. What also important to know, I didn't depict it here, but what's important to know here is that it takes quite a bit of thinking and management to implement secure communication here, and not only secure communication but also secure identity. So this device needs to have certain identity that should be strongly authenticated. So it usually happens that each device has its own signed signature ID or key that only can be read by a central system. So central systems can always identify that data came from a specific device because it's signed by that key. So you can't fake this device and basically plug a raw device and start sending data instead of your device. So that's a general how it generally looks. If we look at the specific implementation, this is an example of implementing the Internet of Things stacks using purely open source technology, mostly Hadoop ecosystem. But I didn't go into the device cloud or in the device's network here itself, but I assume it's just here for now. So what happens here is that we would usually have a MQTT gateway in front, and then the most commonly used sort of event queue is Kafka. I think Gwen was presenting at Kafka earlier today, was she? Yes, okay, so you know what Kafka is then. But basically, for those of you who missed that, it's basically a very efficient, very lightweight, very cost-effective publisher-subscriber sort of message queue, right? You publish the messages through MQTT gateway into different queues, and then subscribers consume those messages in various ways. And you can consume those messages more like batch-style format, in the larger batches to store them into, let's say, some HDFS as I'm using in this architecture, or into the HBase for more real-time interactions, as well as subscribed by more for online stream processing frameworks like Spark in this case, if we're running, if we're designing it on Hadoop. And Spark allows us to produce, to consume those data in a very, very small batches, so-called micro batches, and it has basically a functional programming language, either through Scala, through Java, or through Python, to process those events, and then generate certain insights, which, as I in the previous diagram mentioned, can be routed back to their devices themselves, or can be used in the other system to generate signals like, hey, the car needs maintenance, I need to call the owner, or something else. And the app can be web-based as well, obviously, and interact with the devices as well as with the user. So that would be a Hadoop implementation. Sometimes what we may do, instead of using, let's say, Spark, we may be using something else like Storm, which is similar, not really similar framework, but serving similar purpose for real-time event processing, complex event processing. And instead of HBase and HDFS, we may use something like Cassandra, for example. In fact, we can move that all to the cloud and use, for example, AWS, Amazon Cloud Native Kinesis instead of Kafka as a message queue, and use one of their the Lambda functions instead of Spark here that would generate that would execute the functions. And I'll actually talk about AWS stack in details a little later. So this is how would you custom build sort of this stack, whether it's in-house or in the cloud. And speaking about in-house and in the cloud, many people say, you know, Internet of Things are really the architectures that would really benefit from cloud deployments. And that's partially true. In fact, if you think about it, the Internet of Things data producers are things, physical things, physical devices. So when we talk about deploying physical devices at scale, it's not that easy to have unpredictable growth from 1 million devices to 10 million devices, right? Unless it's like a phone mobile app, then yes, you don't really know how successful it is. But if it's dedicated devices that you build, you know what you build, you know how you send them. And deploying 10 times more devices in one day, it's rather unlikely, right? So you actually know, and you can plan your capacity. When people say, you really need elastic capacity within the cloud for Internet of Things, that's actually a little bit of BS, because most use cases are, you can actually predict that capacity pretty well. So as long as you can provision capacity in reasonable fashion, cloud is really optional. Now, your feature set and can be evolved quite rapidly, and cloud does enable us to be agile. So, but that's not specific to Internet of Things applications. So it has nothing to do with that. Nothing to do with that. So as I said, there's no special attractions of cloud for Internet of Things application, usually, unless they think like mobile, when your use can grow from 100 phones to 1 million phones, if your app becomes popular or things like that. Then it's definitely useful to have elastic infrastructure. So many cloud providers come up with their own stacks for the Internet of Things. Here's an example from Microsoft with their Azure stack. They have a special event hub, which is basically something like Kafka, right? It's also published subscription product, and it's working totally in the cloud, and it's utility priced, I believe, on number of messages that going through that. And they also have the gateway, the MQTT gateway embedded as well. So it's very useful because you don't need to configure that on your own. And then you can connect devices to it whether directly or through this field hub or field gateway through the lower power devices here. And they have a variety of engines behind the scene, like a streaming analytics engine or anything that's using one of the databases, which is SQL Azure, or HT Insight, which is basically Hadoop in the Microsoft Cloud, and work with it this way. So they have a real-time as well as sort of batch-like analytical tools that will help you design those applications on the cloud. The most complete stack and a really interesting implementation of IoT stack is from AWS. In fact, I just been a couple of weeks ago at Amazon reInvent when they announced it, and I was really fascinated what they did, and I'll drill a little further because it was pretty cool. So their AWS IoT component basically includes several things. So it does include the gateway, which is either MQTT or the HTTPS, and that's how messages are passed to and from devices. And they also embedded authorization authentication. But not only that, they really have a very effective way and very automated way to manage the device identities, right? When they have SDK that can be put on those devices. It's completely open, and they have many manufacturers who created devices with that SDK already embedded, and you can buy them obviously from Amazon.com. So what happens with each device, they have an identity. When you register that identity, then your system will know always that this data is from this device. So it's completely transparent to you, and it really simplifies this, identity management that you would have to do yourself. All other IoT stacks that I looked at least the ones I was mentioning, don't really have that embedded capability. So you actually need to program and work on it, which is quite involved process. So what they have after that, through that gateway, the data is routed into two things. One of them is a rules engine, which is not quite the message bus like Kafka, but it's basically a real-time processing engine that allows you to do some basic operations like conditional routing, like counters, tracking, etc. But it's very lightweight, so you don't have to write a lot of things for it. It's very sort of it's defined through configuration, through metadata, and you can implement a lot of basic decisions using that protocol. It's extremely fast, and after that you can send it for additional processing, or you can trigger certain events, or you can trigger certain messages to be sent back to the devices. Another part of AWS IoT stack is what they call a device shadow. But basically what it is a software abstraction to a physical device. Because you as a programmer can work with the device knowing its identity by just calling an API. It's basically like if it's in Java, it'd be like a Java object. They'll have methods, turn on light, turn off light, accelerate, decelerate, things like that, right? So this shadow is basically like a digital abstraction. So when you write your applications, you don't say send message to device to do that. You don't need that. All you say is call the method in the device, stop the water if it's like the device that's controlling the water in your garden. And that's it. And the system will do behind the scenes, send all messages there because it's no identity of the device, stop the water, right? When you want to read something, you can read it from that shadow device, like measurements as well. And it's totally asynchronous, so it will take care of resilient, reliable delivery as well. So it's really cool and really easy to use. So also, if you look at those Internet of Things and how it fits with the rest of AWS stack, that's basically this AWS IoT. And those are all other devices that can be connected through that rule engine, through that stream. And that includes, you can ingest data into like DynamoDB, which is more like NoSQL age-based, or you can ingest it into some of the RDS databases in Amazon, or call Lambda functions, which is basically on certain event, a certain code can be called automatically without any need to manage application stack or and think about scaling it and etc. Right? So it will completely scaling completely automatically. You can route this data to S3 for further storage and later processing and etc. So that's I think the most sort of complete IoT stack I've seen. There's some companies that provide their own proprietary examples. I didn't cover them, and I didn't really research much of them because I haven't seen a single stack become dominant in the industry. So I don't know if they're going to survive, but I think the AWS thing will definitely take off. So now we're all working with Oracle technologies. So what is Oracle IoT Cloud looking like? That's the best thing I could find so far. But a little hard to learn. But Oracle product just sometimes hard to learn. We all know that. That's why we earn what we earn, right? And building systems out of those components is complicated. But seriously, Oracle does have a strategy to release an IoT stack in the cloud. And it's a little bit, based on what I know, it's a little bit like basically have your own, give you the tools that you can easily spin up, spin down, which we know called cloud, and then you can architect your own pipeline and stack out of it. That's sort of what it is, with a little bit of specialization and supporting certain protocols. If you would build something on site from Oracle technology, we know that's how it's going to look like. You will have to have some Exalogic in front of the cloud, which is their middleware, including the service bus, including all this Java thing. You will have to use XML most likely, because that's the best format for lightweight communications, as we know. You might need more racks than one. I just didn't have enough space on my napkin, so I only drew one, so forgive me that abstraction. You will obviously use some Exadata for real-time data processing, as well for some analytics with this Exalytics, which, as we know, automatically does data discovery and produce some useful signals in terms of when we need to fill in the car, simply because I don't really know when I need to fill it in by just looking at the gauge. And we have this big data appliance, which I always misspell as DBA first time I try, so happened again. And that's when we have certain Hadoop distribution that's much cheaper than Exadata. Unfortunately, customers usually never use it without Exadata, so it kind of doesn't really matter. So that's the Oracle approach to that. But like more on a serious note, of course, Oracle has tools that with an Oracle database that can work with IoT style traffic. And in fact, our first, I guess, IoT project was with post meters. You know, when you send mail in the envelope, there's like post meters that just actually registers that mail and then can bill customers, like commercial customers directly, and the post offices and etc. So they had a very complicated stack that included some gateway technology, then SQL Server database, then another SQL Server database, then big data stage cloud, then Oracle database, and then another Oracle database. And they was ingesting those events, and they had an SLA of 5 minutes to end-to-end from the time event produced to the time it's in the data warehouse. So obviously it didn't quite work that way, even though they tried to rewrite it twice. And basically during the day, usually it took them 45 minutes to do that. So when we changed the role, we did put in place Exadata actually, only quarter rack, other than instead of 3 racks of stuff that they had. And we implemented it very simply. Initially we wanted to have a simple just listener through REST API directly get data into the database. Kind of didn't do it because there was some compression involved, so it was a little harder to implement. So one of our big heads wrote a simple Python script, or Perl script was it, I can't remember, that we basically had a minimal server sitting and listening, and basically minimal REST API that was receiving those compressed XML, files, and then did parsing and inserted them into the database as XML actually. And then we know that Oracle has this XML DB thing, which actually can work quite well. You're laughing, I know. It normally doesn't, but if you try really hard, it will work quite well and it will scale quite well. Because since
There's
it was...
no reason why it might not succeed.
That is correct, yes. So, and of course it works on rack because we own Exadata. So we basically process part of the traffic on one node when it comes to ingestion and the rest on the other node because that's what you do to scale in rack. And it worked pretty well, and we basically have the SLAs, we were 99.99 messages need to be within 5 minutes. We had 99.5 within 10 seconds. So what I want to say is that even though I was a little sarcastic to Oracle IoT stacks, it actually can implement very capable systems using those technologies and even much less complicated architectures than I was presenting earlier. So, what else do I have? I think that's, in a nutshell, what I wanted to share with you. Is anybody working with any IoT type project these days? Well, we all know we've been working on them for many years. Give us a good example of what you're working on, Jeff.
Right now I'm working with a company in Detroit, Michigan. They're building drones with 3D printers, and they're doing two things. They're collecting telemetry data on the drones, and they're also collecting the data and video on the drones. So they're building a flight control telemetry subsystem to be able to keep track of the fleet of drones that are deployed out in the field someplace, over a farm, for example, in agriculture, and then collecting the data and sort of doing air traffic control.
So I'll repeat for all of you in the back because you probably didn't hear. So one of the projects that Jeff is working on right now is collecting the data from the drones, telemetry data, the video data to track those drones' fleet in the field and do whatever other processing you can do with those images, whether it's in agriculture or in other field deployments. So that's actually a hard problem to solve because, and the hard problem to solve is actually not on the back end. The hard problem to solve is closer to the front end, because what you have to do, you have to have resilient connectivity from those drones to some central hub or to some field hub device. And depending on the number of drones you have and how quickly they send the data, it may be challenging to have this connectivity going.
So one of the picture you showed earlier, the modification of how classic IoT works, like in this particular case, this is sort of classic centralized, gateway, Kafka, stream it in, and then work on it. In the field where you have a lot of data and you have the users or consumers of analytics are downrange, what happens is you start pushing the analytic computing environment downrange. So, for example, another use case I'm working on is for wildfire management, which is going to try and keep track of firefighters who have sensor data on their coats.
Right.
So the crew chief can figure out where they are if they're
Right.
going to die because the weather changes so fast. So then it's weather telemetry, environmental telemetry from the fire, where the people are, and doing that calculation. It's basically a flight case sitting in the back of a truck. And so there's analytics in the field,
Right.
which is a different topology than what you have.
So basically what it means is that somewhere here, instead of just a dumb field hub sort of field like gateway, you have actually some capacity to store data and process it here locally and do some analytics here locally, partially, maybe aggregation, or maybe then later upload certain results to a central system, because it still happens. And Jeff was just telling a story how he basically building those mini clusters in a box that firemen carry in their trucks, so that they can actually track their data from the sensor from each fireman to see where they are, to see the temperature here, because I remember you were telling me about this project before. Like when there's a fire in a forest, there's all kind of microclimate sort of clouds and areas that, you know, organized by this fire or are coming up because of this fire. And it's really hard and very dangerous to predict where they are and what they are. So when the crew is in the field, you really need those measurements dynamically from all the field in terms of the temperature, the wind and everything, because you need to predict those microclimate. And those microclimate predictions have to happen in the field, because you can't rely on the connectivity from this field somewhere to a central system, because you may be, God knows, somewhere in a wild forest in the middle of California.
So this topology is sort of a hybrid sensor analytic.
Right.
Because even if you have a quad-core ARM64 in your phone, you can do some work. And like you said earlier about time to SLA to realize the sensor data, as soon as you can touch it, you can start working on it. So essentially, the analytics capability can extend right down onto their bodies, because you can't do a lot of work, but the instant you can touch it and start digesting any value from it, the sooner you get the answer. And that, in classic cases, nobody cares.
Right.
That it determines whether or not they die. So it matters to
Yeah.
push the analysis as close to where the data
Right.
originates.
So the classic cases are the ones when we, I guess, can use somewhat unreliable connectivity from the device or from a field gateway to whatever the processing system, right? In the situations like that, or in some medical situations when we work in like surgeries and etc., we can't rely on these things. We have to have 100% reliability and resiliency. Otherwise, we get wrong data, we have gaps, and we can't make proper decisions in what we need to do. I think you're also telling the story how you built Hadoop clusters on the ARM chips to put in the ships in the middle of the ocean, because you need to collect lots of data and send centrally after that as well, which is kind of similar use case, kind of cool. Same topology, yeah. So that's sort of next, one more layer of processing in here, because as we all know, the more complex the systems are, the more money we earn designing it, so it's good. Question?
Not a question. Can I just offer another example? Nothing as close or sexy as what you described.
Please offer us non-sexy example, because we know that Jeff looks sexy.
Oh,
and
yeah. Oh, yeah.
a sexy man. Yeah. Hot like ham.
I work for a hotel company, and one of the things our guests ask us is that when they go to the hotel room, you want the temperature to be a certain temperature. You don't want it too hot or too low. But when you go to the hotel room, you have to set it, and you have to wait until it actually comes down or goes up, the temperature. So what we have done is some of the hotels that piloted that, we actually put sensors in there. And we identified exactly what the guests really want the temperature to be.
Mm-hmm.
And also the lighting as well. Because some people just like the light to be on, the room on, off, whatever. So we collect it actually, and then we analyze that. So when you check into the hotel, your room will be automatically set at the temperature and the light.
I think that's sexy. We need another example.
Will it send a woman in your room when you check in too, if it's in your preferences?
We're not programmed right now.
Okay, but this is a cool thing, because this is basically an example of how home automation gets sort of commercially applied, but it's actually much harder than just doing home automation, because you need to personalize that based on the guest, and the guests are rotating quite frequently. So what it means, you actually need to manage not only identity of those devices, but identity of the guest as well. So it goes beyond the IoT use case, but I don't know if you heard in the back, basically Rup was talking how they designing those systems in the hotel chain that he's working at in order to automatically set the temperature to our preferred level when we enter the room, for example. Ideally, I'd like to do it 10 minutes before I enter the room, so you want to track my proximity somehow.
No, you don't. So when you check into the hotel, the front desk, it triggers it.
Yeah, so on check-in it knows that I'm Alex and I like it really hot. Okay. Sounds good. We'll also set the shower temperature for me.
No, it's not the light.
Call me when it's done. Any more questions? Examples? Here's another one.
No, I have a question. I'm interested in what
So there are multiple examples. I can give you a few. Have you seen Kellen's presenting this photo bearer, which has like Raspberry Pi, I think, inside, or Arduino, which are basically automatically making photos and posting them on Twitter. It's not quite Internet of Things, but that's often a style of device. It's kind of Arduino, a little more specialized sometimes, because Arduino is just consuming too much energy, even for the field device. So it's something like small boards usually. That's for things like home automation. That would be a good example. In fact, I'll tell you the truth. The way that the session was supposed to go until Sunday was totally different. Because the plan that we had, maybe we'll do it one day, but what we were basically doing is we were designing the mobile breathalyzers. So we've got sensors and everything, and we've got one hardware component missing, and we couldn't find it. So that didn't happen. But the idea is that we would basically go around with a Raspberry Pi device, and you breathalyze.
Oh my God.
And we will measure how many of you are actually sober here. Which is, I know, will not be close to 50%, but hey, I wish I would be speaking on Thursday about it, then definitely it'll be 100% non-sober after the Treasure Island event, but hey. But Jeff, there's other devices which are more specialized, have a longer range, and etc. You have examples?
Tethered balloons.
Yeah.
So that's, again, they work under certain circumstances, and one of the things, in a wildland fire up in Illinois, if you're in an urban interface where you're doing sort of public safety drones, then and this is not well understood either by the FAA or any administration that manages airspace in the country. This whole low altitude, too many drones flying around problem sort of caught them by surprise. So then you have to be careful about what you stick up in the air, not just your drones, but then having tethered balloons in order to do repeaters. And it can be wireless repeaters. It doesn't have to be rocket science complicated. One of the things we're trying to do is use cheap off-the-shelf repeaters, but that's one example. Sometimes you can just have wireless on a truck that has an antenna, a really high gain structure in the antenna array, so it's not just a wire that hangs on the top of the truck, but then you get more range, and there's practical limits to that.
They often build specialized mesh networks that basically mesh architecture networking that has multiple redundant nodes because they know that they're going to fail because there are way too many of them and they're very too unreliable, whether it's balloons, whether it's stuff in the forest. And
so this term from the military space called self-organizing networks, and they make radios that do that, self-organizing.
Yeah.
DARPA did an example of situational awareness, and they used self-organizing network radios. They're crazy expensive because they're military components, but that's also an example of if that technology became a little more prevalent, it would be affordable for commercial use. But that's a DARPA example.
one of the things, if you're interested more about specialized Internet of Things protocol, the company I think who is ahead of everybody commercially is Cisco. They really work hard on it, and they have a variety of protocols that they're working with, and at least they have, I think, best coverage that I've seen. There may be some others too, maybe more aggressive and new entrants, but they have a good material about that. So if you Google Cisco IoT architecture, there's like YouTube videos that actually gives you a quite good understanding what's the specific problem for those devices, and then they tell you about the protocols which are designed for very low power transmission, that are designed to route packets differently, the different routings than just IP4 protocols, IP6 protocols, and etc.
So the customer in Detroit is, Cisco is building the fabric, the IoT fabric, and then I'm building the back-end platform and trying to figure out how we do telemetry and old-fashioned methods. So we are working with them. They understand the networking piece. They really can't spell data. It's really weird, but they just sort of, they're a hardware company and they make switches, and so they do the fabric piece, and then the data flies in the building, and then they're like, that's not our data, so how do we do that? So they are building fabric for the aircraft manufacturer.
Most of the companies either can spell devices or can spell data, so there's almost no company that can spell both. I think Amazon came as close as possible to that with their complete stack and complete integration, and they actually partnered with hardware manufacturers who produce those end devices, but they still, I think, far ahead. Google has their own project, Brillo, with their own Weave protocol, but it's not out yet, generally available even better. So, but it's coming, I think, in Q4 this year.
And Alex mentioned it earlier, but these are really hard problems because everything goes wrong in the field all the time.
Yeah.
So it's very difficult.
More questions? Well, that was fun. Thank you.